In this video, we're going to look at vectors in space, which is just a fancy way to say 3D vectors. We have been looking at vectors that were on the 2D plane, so just an x and a y. Now we're going to be looking at x, y, and z. And the good news is everything that you did before with just x and y, you basically just do one more time with x, y, and z. So it's not really as bad as it seems. You just have to do everything 3 times instead of 2 times. And you'll see that's the same thing for your distance formula, where before it was just x and y. Well, now you have to do the same thing with z. And so instead of just having -2, 5, you have the 1 for our z coordinate. My second point is 3, -4, 6. After you get done doing x and y, just toss on your z, and then you're good to go. And you take the square root. That's still going to be called our magnitude. Finding the position vector, it does not change at all. All you're going to do is subtract those two and then leave them as they are, and do it one more time for z, which is now k or k hat, depending on how you're writing it. And it's the same for the unit vector. Before you divided the x and the y by the magnitude, and now you'll divide x, y, and z. So all of the unit vector, position vector, distance formula stuff doesn't really change at all. Now the dot product is going to go one more step from before, and we're going to be able to do some other kind of cool things that we were able to do. So the dot product, remember, is kind of this multiple multiplication that has to do with an effect size, not necessarily where you're going. And hopefully you were able to read through some of this short article about what it means to be dot product. And they give this little image of a 2D one, where you're not actually working with the vectors, but how you got to that vector using the legs, if you will, of that right triangle. And you're going to get a value that really just winds up being what the two parts that are going the same direction, what that increased speed would be, and then adding it to the other. Because these, as you'll soon see, these are perpendicular, and so that's going to wind up undoing each other, and then we call that orthogonal when you're in the vector world. So a couple of different ways to think about a dot product. The first example they give you is a solar panel. So you have your solar panel and it's facing a certain direction, and as the sun moves through the day, sometimes you're going to get a better or collect more energy, if you will, depending on how this ray is coming in. This is fixed, this moves, and so the combination is how you figure out how much energy you can collect. And I think this kind of makes sense, and you can kind of see this with like Wi-Fi signal and just even TV reception. If you have any kind of satellite, right, you want to point it a certain direction and try to collect the most of it that you can, depending on how everything is facing. But I think probably the easiest way to think about a dot product is Mario Kart, right? So you have your guy that you're driving, and you're going a certain direction at a certain speed, so you're following this vector path, and you're going to hop on one of these boost pads. And the boost pads are fixed, and it's saying you need to go this way, this fast. And so when you drive over it, it doesn't just boost you in the same direction you were going, it pushes you at this speed in the direction you want to go. So you kind of come out somewhere in between, faster than you were going, but not quite the same direction. Another good example would be like when you try to swim in the ocean and you're trying to go one direction and the current's trying to push you in another direction, and you kind of land somewhere in between. It doesn't so much talk about where you land, but what the effect of doing those two things at the same time is. Like what is the almost that magnitude of how fast you were going times how much faster you are going from there. It's kind of if you think in terms of algebra, like a percent of increase on top of something that has already increased, or a percent of a percent, like 50% of 80% of the people. You hear stuff like that a lot. So that's what a dot product is. And now you just are going to look at it one more time in here with 3. So still very much the same situation that you were looking at in 2D, even the angle between the vectors. What's a little bit new is the direction angles, because now we have an extra one. And so we'll be looking at how do we open these up so that my one vector really has 3 angles that are taking place. And so what I usually describe this as moving an antenna. So if you have an antenna that's pointing just straight up, which we will call a normal vector, something that's shooting right out of the origin, if you will, at one axis going right up, and it's 90 degrees to a particular plane. If you look at something, it'll look something like this, right? So you're imagining this, and then you're going to open from here up a certain way, over a certain way, and then back or forth, right, for our third direction, another way. So I have these 3 angles so that you're pointing somewhere in space. So think about moving an antenna around like something like this, where you can move it left, right, forward, but you could sweep in between also. And so that sweep in between, or back and forth, that's how you're going to get your Z. So you have everywhere in here that you can hit. And the formula looks a little bit scary, but it's actually pretty easy when you think about this. It's just your magnitude that you're going to find, and then that is going to be the denominator for the particular component that you're looking for. So instead of saying something like negative 3i plus 2j plus 6k, I want to talk about this much like I want to take this car direction, go back over to a plane direction, turn this far, and go this much forward. So you're going to start off with finding your magnitude. Easy enough. 9 plus 4 plus 36. Take the square root of the 49, and it's a 7. Now, usually they're not nice, but this one turns out to be a nice one. So that's going to be the denominator for everybody. So instead of saying go over negative 3, I'm going to say open up this amount of an angle. And what is that angle? Well, the cosine of that angle has to be the negative 3, because that's how far you walk. That's your x part of your coordinate, over that hypotenuse that you were looking at. And so what angle has the cosine of a negative 3 over 7? And then you're going to do that for each one. So for the 2, instead of saying go over to the 2, how far up would I need to go? I don't know. I only have the cosine, but what would be my output of the 7? Well, that's going to be what angle has the cosine of 2 sevenths. And then finally for your last one, negative 6 sevenths. And one by one, you would say inverse cos of negative 3 sevenths, inverse cos of 2 sevenths, inverse cos of negative 6 sevenths. And you'll get 3 probably not so nice looking angles. That's all that it is. It looks very long, but it's really not that bad.